Hey guys, it's Tina right here,
And Leslie.
and we're going to explain to you how exercise for the review sheet works. So it says here, after falling from rest at a height of 30 meters, a 0.5 kilogram ball bounces upward, reaching a height of 20 meters. The contact between the ball and ground lasted 20 milliseconds. Find the average force exerted on the ball by the ground. So, so we're going to break this problem into different steps. As you can see here, um, this is the ball. Imagine you dropping the ball and this is going down. It's accelerating downward. So this is going to be step 1. The step 2 is going to be when it's contact with the ground, so it's hitting the ground. And step 3 is when it's going to bounce up.
Okay, so for step number 1, it's the fall. So we're just gonna write fall here. So we note the initial velocity because it's falling from rest. So the initial velocity would be 0 meters per second. And we know the change in displacement will be negative 30 meters because it's going down, and they're saying it falls from rest at a height of 30 meters. So it's going from here down here. Yeah. And the final velocity that we don't know yet, we don't have the time, so we don't worry about that one. And the acceleration we don't know, but it's easy to find the acceleration because we could just draw a force diagram. So we have gravity going down the ball when it's falling down, and we know the mass of the ball is 0. I'm sorry about that. Okay, so the force diagram looks like this: force of gravity on the ball acting downwards, and that's going to be positive, that's going to be negative. And we know the mass of the ball is 0.5 kilograms, so then we can times this by 10 because we know gravity is 10 times mass, so then that would be 5 newtons. So then if we know that, we can easily use this equation: A equals F net over M, and that would be Fn over mass, which is 0.05, and that's just negative 10 meters per second squared. So then we know what the acceleration is, and it's negative 10 meters per second squared. And then Tina is going to take over.
So now that we have all these things, we can go to the on this worksheet. If we go to where the kinematic formulas are, we see that we can use the last one because we have velocity final, velocity initial, and displacement. So we go. So us using this formula would be velocity final squared equals velocity initial squared plus 2a displacement. It would be velocity final squared equals 0 squared plus 2 times the acceleration, which is negative 10, and times negative 30, which is the displacement. Then we do velocity final squared, square root. We just finished this. Plus minus, it would be plus minus square root of 600. And velocity final would be equals plus minus 24.49 meters per second. So because the ball is going downwards right now, so this would be positive, this would be negative, then it would be the same here, negative and then positive. Because it's going down, we don't use the positive, so we use velocity final equals negative 24.49 meters per second.
All right, thank you, Tina and Leslie. I'm going to carry on from here because they had to go to class. So far, we know from the falling part that at the very end, they were going 24.49 meters per second. I'm going to take out the square part there, meters per second downwards. And let's take a look at the middle part now. I'm just going to erase this section so I got a little bit more space to work with. So looking at the middle section, I'm going to do two things. I'll separate it with a line and also do it in green. So this is, section number 2, and I'm going to say, let's see if I can get this to work. This is while in contact, while touching ground. So it's this part right here. So one thing is it's going to be for a period of, it said 20 milliseconds. So that would be, milli is 1,000, so it would be 20 over 1,000, so that's 0.02 seconds. Now, I'm going to do the same kinematic stuff here, and hopefully it'll make sense in a second. What are all the things we know? Oh, we got the time already. Okay. Okay, so at the beginning of this period of time, how fast is it going and in which direction? Well, the end of the fall part is actually the beginning of this green while touching the ground. And so to begin with, it's going downwards at 24.49. So I'm going to put this one as negative 24.49 meters per second. At the end of this, it's going up because it's going to bounce. And I don't know how fast it's going to go yet, okay? And this delta x, the displacement, is a little bit hard to think about. I kind of like the way that they drew this section where the ball kind of gets squished. So there is a little bit of motion. The center of the ball maybe have been here, maybe been in the middle here. I'll try, maybe it was red. Maybe it was there, and then the center of the ball goes down, and then it goes back up again. So it actually does do some changing of position, but it's not something that's going to be easy for us to figure out. But the whole point of calculating all this is that we want to figure out the acceleration. Because if we can figure out the acceleration, that's where we can bring out our friend like F net equals ma, and we can find out some information about how the ground was pushing on it. So I'm going to kind of have to leave this hanging for a little bit, because when we think about it, this final velocity of the while touching the ground segment is the same as the initial velocity for the rebound or bounce up period of time. So what I'll do is I'll follow their kind of schema here, and I'm going to switch to blue, and I'll go over here and I'll say 3. This is the bounce up period of time. Okay, so the bounce up, it was going up at some speed, and this is really what I want to figure out. At the end of that bounce, it stops. So once it gets to its highest point, it's like this ball's at the ground and it bounces up, right? And it kind of goes like this. And at the very top, it's not moving anymore, so I'll say 0 meters per second. The acceleration, it's going to be the same thing as that first acceleration of -10, because the only force acting on it is gravity. The time, I don't know. The delta x, well, again, it's starting from 0 and it's going to 20 meters. So my delta x is going to be equal to positive 20 meters. So I want to find the initial velocity, so time is the one that I don't need. So it's just like that same formula for the first one, just like how, I'm not sure if it was Tina or Leslie that stroked out delta t and they picked that equation. I'm going to use that same equation. I'm going to say Vf squared, the final velocity is the initial velocity squared, plus 2a delta x. So if I plug in my numbers here, I've got 0 squared equals vi squared plus 2, I forgot an acceleration here, 2a delta x. So 2, and the acceleration is -10, and the displacement is 20. So I'm going to get 0 is equal to the initial velocity squared minus 400. So if I add 400 to both sides, I can say 400 is equal to vi squared. And now when I do the square root of both sides, vi is equal to plus or minus, what's the square root of 400? 20. So just like before, I have to think about, well, what is the sensible answer? Is it at the end, or at the initially when it was bouncing up, was it going up at 20 meters per second or down at 20 meters per second? And the answer is positive. It was going positive 20 meters per second. So the initial velocity from that bounce up turns into this this final velocity that I had over here. So I'm going to take this number and put it over there once I switch over to green. So here I'm going to put in 20 meters per second. So my goal was to figure out acceleration, and I'm almost there because now I have enough information. I've got time, initial velocity, final velocity, and I've got to figure out acceleration. The one that I'm not using is delta x. So if I think about here, I'll make some space again. If I think about my formulas and which one doesn't use delta x, doesn't use displacement, it's that fourth one. It's Vf equals Vi plus a delta t. But honestly, it's a lot easier, I think, just to think about the definition of acceleration. Acceleration is the slope on the vt graph, or it's the change in velocity, that's the rise, divided by the run. These two formulas are actually identical, they're just rearranged. But since I'm solving for acceleration, I may as well use the second one. All right, how much does the velocity change by? Well, be careful. The answer isn't 4.49 when you look at these two. The change in velocity is going to be the final one minus the initial one divided by how much time that goes by, which is 0.02 seconds. So the final velocity, I'll make some space again, the final velocity was 20 minus negative 24.49 over 0.02. So you see how the subtracting of the negative business right here, those two are going to turn into a positive. So when I punch that into my calculator, I get an acceleration of did I get this right? 2224. Oh, I put the decimal in the wrong place. 2,224.5 meters per second squared. All right, so you know what, we're so close. Let me just go back and read what is the thing that we're supposed to find out. So it says here, find the average force exerted on the ball by the ground. Well, when I'm starting to think about forces, always a good thing to draw a force diagram. So, and this is during this green period. It's this period when the ground and the ball are in contact. So just during that period of time. So what's happening? Well, I've got a force of gravity downwards. And I believe we already found out that that force of gravity was 5 newtons. And then I have a normal force. And the normal force is going to be very large. And the reason why the normal force is very large is because I know this thing's going to be accelerating upwards at 2,224.5 meters per second squared. So in other words, I'm going to have a very large net force up. So there's two ways to think about net force. One is that F net is equal to m times a. Hey, let's just figure that out right away. 0.5 multiplied by this large acceleration. So this is going to end up being, hold on, 1,102.25 newtons, and that will be upwards because that acceleration is positive. It's the ball's accelerating upwards. And so the other way to think about F net is you can also say that F net is equal to the sum of all the forces. In this case, I've got the normal force up, and I've got the force of gravity downwards. So which force do we want to solve for? Going back and reading this one more time, the average force exerted on the ball by the ground. That is what normal force is. So this is what we want to find out. So if I rearrange this to solve for normal force, it's going to be Fn is going to be equal to F net plus Fg. In other words, the normal force has to be 1,112 newtons more than 5 newtons. So it's just another way of saying we're going to add these two together. So 1112.25 plus 5 is going to give us our answer of 1117.25 newtons. At the end of the day, I might say, well, how many digits do I really need to keep? And I'm looking, I got a 30, I got a 0.50. I think I'm going to only really need to keep 2 decimals. So if I was to think about this, it would be 1100 newtons is about as accurate as we can get from all our answers. But I'd be looking for the extra thinking just to see, did you add that 5 at the very end when you thought about the normal force instead of F net? So both of these I would be very happy to see on your assessments. All right, so I hope that was helpful.